Hello and welcome. My name is Mark. This is my first video on this channel. I wanted to do a follow-up on a video a day or two ago by my colleague Matthew. So we have this benchmark, CPU benchmark, that is based on computing a sum of squares with one or more workers. So Matthew did a C version, but we had a Python version before, and this is a trace capture with the Python version. As you can see, using one worker, it would take a certain amount of time, and scaling up to, for example, 4 workers, it would scale up pretty well, taking just a little bit more than a fourth of the time versus one. So this is because this benchmark is meant to be purely computational, and so it will scale really well until you reach the number of physical CPU cores you have on your machine. In my case, it's 4 for a total of 8 cores. But if you notice, 8 cores takes virtually the same time as 4, maybe a bit longer even. That is because the horsepower is really in those 4 physical cores, and with this type of workload, it's really the physical cores that are important. So when the C version came out, I captured a trace, expecting to have something pretty similar as far as scalability goes, but instead we got this. Here, one worker versus 2 versus 3, 4, it did not really matter. The time taken was roughly the same no matter what. So it looks like maybe there is another bottleneck that makes it so that we cannot really benefit of having more workers. Let's look at the code a little bit to try to see how it works. So this is the structure at the core of the benchmark. When we divide the work between one or more workers, each worker will receive its work orders. So the computations, each worker will have a chunk of the total computation that needs to be done, indicated by the start and end values. We have the result and the time taken that are also updated in each worker. So let's look at the diff. When I looked at the program, I validated the logic. Everything seems good. So I ended up at the deepest part of the program, that is the thread code or the worker code. So I had a hunch that this here in the computational loop might be the bottleneck. So we're using the result field of the structure that we just saw that is passed to each worker, and we update it in a loop each iteration. So I tried to make it instead a thread local variable and use that for the update, only to copy the final result back in the original structure. And when I did that, I took another trace, which we have here. And we can see that we are back to having a good scalability, similar to the Python version. One worker would take a certain amount of time, and 2 workers would take roughly half that time, just slightly more than half, and 4 would take just slightly more than a fourth of the total time. But adding more than 4, more than the number of physical workers I have, cores I have on my machine, would not really improve the situation further. So what happened then? How did this little code change help? Well, here's my theory. So let's go back to the more recent version where we use a thread local variable. So the structure here that each worker, each thread receives, it is defined in the main program as an array. So each worker will end up having its own instance of that structure as part of this array. The array is passed to the work dispatcher. The work dispatcher is the one that will figure out the work that needs to be done by each worker, updating their own instance of that structure, and in the end creating the thread and passing their own instance of that structure. So because all those structure, even though they are each thread as its own, they are defined together in an array. They will be really close to each other in memory, which means that they are likely to share a cache line, meaning that there is a good chance that every time one of the threads will update its result in that loop, it will invalidate that cache line. I don't know whether when we have 8 threads, if they all share the same line, but it doesn't. It might be so. It might be that there is only some sharing among some of the workers, but in all cases, it seems to create a huge memory bottleneck, or that's my theory anyway, rendering adding more CPU resources useless to scale this particular computation. So that's my theory, and the results seem to demonstrate at least that this little change helped quite a bit. I wanted to mention though that well, some people might think that it doesn't really matter to go into this level of detail, because if you just ask GCC to add optimization to your program, it will do it for you, and there is some truth to that. Once I turned on GCC optimization, not only was this bottleneck lifted, but the execution time was divided by something like 3. However, I believe that it's still very valuable for a programmer to know how to identify and lift bottlenecks. So even though it's very nice if your tools can help with it and do it for you, like GCC apparently is able to do in this case, and more. So yeah, that is it for today. I hope this was interesting. See you next time.